Verstanden. Ja.
Verstanden.
All right. Oh, I've got to hit got it. Got it.
Very interesting. Should we give it 2 more minutes or should we start? What do you prefer?
We can give 2 more minutes.
2 more minutes, okay, we'll do that. Where are you from in Italy?
I'm from the southeast.
Southeast, yes.
From
Okay.
I'm very famous.
I see. You're very close there. You're on the Adriatic coast, yes. Okay.
Very close there.
That's nice.
I'm myself on the coast.
Okay.
I don't know if I could have a mic or.
A mic is good, actually, yeah.
Or can you hear me? Or
No, it's also helps the speaker, the Zoom hear you.
all right.
Okay,
It's a minute.
well,
When
you wouldn't think that a quantum spin liquid does anything to the resistance, electrical resistance, but we're going to find out today from Raffaele that can tell us about electrical quantum probes of quantum spin liquids drag resistance mediated by quantum spin liquids. So we've got half an hour here.
Thank you very much. Thank you also for the intriguing introduction because it's true. Hello.
We're going to
All right. All right. Very good. So as you said, we can expect electrical transfer probes to work on quantum spin liquids. However, in this work, down to the video and Alex Lerchenko, we explored non-local. So the trick is in the non-locality of electrical probes to sort of get some insight on the signature of quantum spin liquids. And so let me get started with some motivation. So we had some talks about theoretical and the theoretical, but actually the first, if I'm not mistaken, don't kill me if I'm mistaken. So
Going in and out, you've got to adjust the mic somehow.
I will put it further away.
Yeah,
not
put it
close.
slightly down.
if I know Martin, you shouldn't.
You're gonna try the other one.
Put it slightly lower.
Is it on better?
No. Just put it slightly lower.
No, I think you've got to unbutton the show.
Yeah, that should be.
Is it better?
Yes, all right.
All right, no, I'm not sure. Anyway, so what is a quantum spin liquid? Usually, so the 2 main characteristics of a quantum spin liquid that are interesting for the purposes of this talk are fractionalization. That means if you start with a spin system, for example, anti-ferromagnetic Heisenberg model, you can rewrite the spin using these representations using F dagger and FR fermions. And so in this sense, the spin is fractionalized. You see this comes with some liberty of phase choice. And this is not the whole story because you also need to impose a constraint of single occupancy that I didn't write here. But so this combination of fractionalization, so this representation of the spin and the constraint of single occupancy is what factors in for the emergence of H fields. And this operator F is the operator of a spinon, and so it carries spin, and it's it doesn't carry electrical charge. So why are these systems interesting? So from a theoretical perspective, there's an interesting topological order, right? So on the left, you see the model of the toricos that I already mentioned, and this model. So this model has topological order, which is a new kind of order, so a non-local order. So that means that you don't rely on the definition of a local order parameter, as in the paradigmatic Ginsburg-Landauer theory. And this is interesting, especially as we see in topological quantum error correction codes. And so here on the left, right, I said, yeah, okay. On your right, sorry. On your right, you see the Sigma chip, and Philip is not here, so it's gone. And however, on the experimental front, so there are some materials such as, wait for it, yes, such as alpha ruthenium trichloride, 1 times on the diselenate, and 1 times on disulfide, that are candidate materials for hosting quantum speed liquid phase. And these materials are exfoliable. So see in this picture, 2p layer of alpha ruthenium trichloride being laid on a substrate, and here single layer 1T tantrum disulfide, right? That's it, sorry. And that sort of has this emergent structure of local moments that arrange themselves in a triangular lattice. And the key thing is that the fact that these materials are exfoliable gives rise to new experimental probes. So new, we can probe the two-dimensionality of these quantum speed liquids. So what has been done before, there have been some proposal for spin current driving, and here on the right lead, there's some polarized current, and some current that gets polarized and gets injected in the quantum speed liquid candidate material, and voltage is measured, and from this BI characteristic, you can some sort of deduce a signature of different kind of speed liquid. There are thermal probes proposed, which for the thermal conductivity, you get some sort of signature of the fractionalization of the spins. And there are also some STM experiments in which you tunnel current and probe these 2D materials. However, our proposal goes in this direction, and we propose we said we're going to use electrical probes. How do we do it? We propose a spinon induced drag experiment that we look now. Pay attention, because the setup is sort of complicated. It looks sort of like this. So there is it's a sandwich in which the bonds are metallic, and the quantum speed liquid is a vegetable, doesn't conduct charge, and however, you can sort of it still couples to the layer, and you will still be able to transport momentum. But before we go to that, let's go to Coulomb drag before. So in a Coulomb drag experiment, very quickly, let's review what it is. Two metallic layers are interfaced. And what happens is that you drive a current through, say, the upper layer, and through Coulomb's interaction, you the upper layer, so the charge carriers transfer momentum to the charge carrier in the lower layer, and the lower layer develops voltage. And these two quantities, so the current and the electric field developed, are proportional. Just this proportionality constant is called drag conductivity. And what is interesting is that, so you see the plot of the drag resistivity against temperature, and what the main object of this study is the temperature dependent of this proportionality constant. And you see that for Coulomb drag, in the specific case of Coulomb drag, there is some low temperature T-square behavior. Then there is this TD is a temperature scale that is defined by the spacing between the two plates that gives the sort of maximum momentum that can be transferred, and then it becomes T-linear. So in our case, we take inspiration from this, and now you see a more realistic realization of the actual experimental setup. So you have you have a quantum spin liquid layer sandwiched between two metallic layers. While for Coulomb drag, you have just one step process of momentum. So electrons are accelerated, they interact with Coulomb interaction with the other electrons in the lower layer. Here you have a two-step process in which the upper charge carriers are coupled to the quantum spin liquid, and momentum. So the momentum will be transferred, relaxed, and transferred again. And the forcing term, so the current injected, will be proportional to the measured voltage through, again, the drag conductivity. We are actually interested in an object that is proportional to the drag conductivity, which is the this 1/τd, which is the drag relaxation time. How did we tackle this problem? So you need to have a mathematical apparatus that allows you to account for momentum transfer, momentum relaxation in the different layers. You see the answer right here on the side. So we use the Boltzmann approach. Yes.
So can I ask the question that Piers started with? So these arrows don't represent electrons.
Represent momentum.
They represent, but why doesn't the spin liquid notice an electrical current in the bottom left?
Well, because so the how they coupled, I discussed. So they're coupled through Coulomb interaction, and so it's a basically spin-spin interaction, and the spinons here sort of carry memory of the preferred direction, in this case of the lower layer. So in this sense, and they of course also for the.
So it is actually a mechanism where kind of for very short times the electron does touch the spin liquid, but then it comes back very quickly.
Yes, exactly.
Can I ask a conceptual question? Of course, I understand the spin liquid is translationally invariant and therefore momentum is a good quantum number. But how do you understand an object that is neutral that can carry momentum? I mean, how can if I think of it semi-classically, you're kind of implying that it's got a mass and a velocity.
I mean,
Would that be true in a spin liquid?
I think of condylattice. In a condylattice, you sort of have. So if you start from lattice with Heisenberg interaction, then it's possible that you develop. So in condylattice, you have translation invariant. So you have momentum. You can have dynamic. So it's just that this dynamic is not connected to charge conservation, but to this the conservation of this constraint of numbers.
Let me try this another way.
Yes.
Momentum is carried by particles microscopically,
Yes.
right? But no particles moving in the quantum spin liquid. So how can it possibly?
No, well, no. Okay. Now I think of something else. So no, not for the gapless, at least the gapless quantum liquids, which are at least of interest here. So how I understand it, the easiest way for me to understand it, for example, the resonating valence for example. In that case, okay, you have some excitation index. So that excitation to the massive superposition of all possible single can resonate between one possible combination. So it actually effectively is one particle moving and carrying energy.
I like the idea, but I won't have it way more precise. I'll talk to you after the call.
All right. Yeah. Thank you. Yes. So as I said, we need Boltzmann. And okay, first of all, let's discuss what kind of model we are dealing with. So we treated U1 quantum speed liquid. It's important to stress that they are the spinons are gapless and they have a Fermi surface. And so the U1 quantum speed liquid has, of course, U1 gauge excitation that give rise actually to a non-Fermi liquid. And this complicates a bit things. While for the D2 quantum speed liquid, while being more exotic in the literature, and gives rise to a Fermi liquid phase with gapless spinon and Fermi surface. So the question is now, how can we use Boltzmann for us? Let's read together. I spoiled it. So the question is, how do we use Boltzmann for non-Fermi liquid? So non-Fermi liquid, basically, we don't have well-defined quasi-particles. So while for Fermi liquid behavior, you have a spectral weight that peaks very sharply and the dispersion relation. The interactions of the gauge fluctuation, like in this case, for the U1 quantum speed liquids are so strong that this, despite going down with temperature, this peak remains so large that you cannot have long-lived quasi-particles. And this is in principle, one could say, so actually people say that you cannot use Boltzmann for this kind of systems with no well-defined quasi-particles because Boltzmann is basically semi-classical, so you need to have this picture of scattering, multiple scattering particles. How do we use Boltzmann? We went back to, we follow the Kadanoff range procedure. How does this work? So for this system, the self-energy is just dependent on the angular part of momentum and on the frequency, which means that actually the whole of the propagator, so the spectral function becomes peaked at, so instead of seeing it as a function of omega, we see as a function of the dispersion relation. And in this direction, it's peaked, yeah? It's very well peaked. And this allows for the definition of what is called the pseudo-distribution pattern. So you can still apply all the usual Boltzmann machinery, but the trade-off is that you have to deal with particles that have weird kinematical constraints, as we will see even there in a bit. So as anticipated, the interaction is mediated by Coulomb coupling, and to tame the fluctuations, large N approach is needed. So that N is for large N, and the formalism we used was Keldysh formalism, in which you sort of have contour, time contour from minus infinity plus infinity and plus infinity minus infinity. And then you can connect this to rotate it into Keldysh space. And there is a way, yes.
Sorry, just to check, is the large N SUN, does it apply to the spin and the conduction electron? What's the N?
So the N is the number of N applies to the spin. Yes. So
but spin of both types of fermion?
Yes.
Yeah.
I get, yeah. Anyway, yes, okay. And so there is a way to sort of connect, to sort of derive a collision interval to connect it to the self energy. And so here the sigma is the self energy, and Keldysh, retarded, and advanced are respectively K, R, and A are respectively Keldysh, retarded, and advanced component. So based on this, we were able to describe how momentum is transferred. And the system of equation, so here you see a cartoon representation of the setup. Green refers to the metallic plates, blue to the spin, to the quantum spin liquid, so the spinons. And on the top left, there is the forcing term. And on the bottom right, there is this minus delta F3 over tau 3, which is basically delta F is the deviation from equilibrium of the Fermi distribution function, and which means that we treated the relaxation within the layers in a relaxation time approximation. So writing the relaxation rate as minus delta F over tau, and the momentum transfer using this collision integral derived from the self energies. And solving this set of equation, we could find the drag relaxation rate, 1 over tau d. And it's an empty formula, but you can see that. So the green part, so you have the imaginary part of the polarization operator, both for layer 1 and 3. Yeah. And which means that we will excite particle Hall first. And here in blue, there is in the interval some information related to the distribution function of the quantum speed liquid, of the spinons in the quantum speed liquid. And it's all contained in this E2. Information on how momentum is relaxed within the quantum speed liquid is contained in tau 2 over there. And while you also see at the denominator, there are some hyperbolic signs that are soft frequency cutoffs, and so their temperature, of course, plays a role in cutoff of the this integral that defines the drag relaxation rate. Now, let me show you some results. We start with zeta2 quantum speed liquid. So also this tau 2 and I2, these terms here, I should have said, are what distinguish the zeta2, the Z2 and the U1 quantum speed liquid. And yes, so we start with the Z2 quantum speed liquid, and we calculated the drag relaxation rate in a variety of regimes. So in these regimes are defined by the parameters, so Fermi velocity, Fermi momentum of both the metallic lead and the quantum speed liquid. Here you see, okay, the result for a symmetric case in the sense that the Fermi velocity and Fermi momentum of the bottom lead are the same as the ones in the third lead, in the upper lead. And this graph will refer just for one step of the momentum transfer. So in this first regime, you see, so on panel B, you see the support of the interval for the calculation of the 1 over tau, so drag relaxation rate. And the support is given by the intersection between the particle continuum of so the kinematic defined by the kinematic constraint of the metal and the quantum speed liquid together. And you see that there is this TC appearing, and it's a crossover temperature. So there is a new scale of temperature for which if T is lower than TC, so if we move it below, it alters. So T, as I said, it's a cutoff. You can see it as a cutoff. And if you move it below, it changes the support of the integral. And while if you go above, nothing happens. Basically, it's this. And this phase argument. The phase space argument is sufficient to explain the crossover in temperature. So on panel A, we plotted the drag relaxation rate against temperature. And so you see a crossover from T squared to constant, T to 0. And you lose 2 powers of T because this is actually a 2-step process. So here it's just described as a 1 step, but you have to keep in mind that 2 steps. So each step you lose 1 power of T. And so the situation, while the situation for this regime is that, so here I can actually point. So here you could also possibly define a crossover temperature, but actually you're bound by the Fermi energy. So we always dealt with temperatures that are smaller than Fermi energy. And so here you actually don't see any crossover. You just keep the T-squared temperature. For the Z2 quantum speed liquid, the situation is symmetric. And now we turn to the U1 quantum speed liquid. So whatever you see on the left, the vertical line, is the particle continuum for the spinons. And so you see it different than this. So you sort of have any frequency that you can excite while the particles are in the Fermi surface. And the situation is different for 2 reasons. First of all, you lose this symmetry in phase space, and so you only have two possible regimes. But the situation is similar, also in a sense, because so also here you can define a crossover temperature, and you can go with temperature below, and it happens. So there is some extra temperature dependence, but here this sort of becomes you lose 2 powers of T. And also notice that of course also the scaling behavior is different, and this has to do with what the first of all what the tau2 is, so how momentum is relaxed within the quantum speed liquid, and there could be different mechanisms. And this result of this suspicious power law, so T to the 8/3 and T to the 2/3, comes from the mechanism that is spinons relaxing momentum into thermal bath of H bosons. And so here we are, we can jump to the summary. So I told you about U1 and Z2 quantum speed liquid. We proposed this new item on the menu. We also did calculations that I didn't present for Z2 key-type, so quantum speed liquid. But so let me summarize everything. So we find that for the Z2 quantum speed liquid, we have a symmetric situation with this corresponding regimes and scaling behaviors for drag relaxation rate. And for the U1 quantum speed liquid, we lose this symmetry, and we have this power law behavior from 8/3 to 2/3 for the drag relaxation rate. That's it. I will thank you for your attention, and yes, happy to answer your questions.
This, thanks. Could you just go back to the slide where you were showing us these diagrams for the U1? Yeah, exactly. Yeah, here. So I didn't quite understand panels B and D is because I was expecting there to be a second shaded region.
Yeah. So there's yeah, my mistake. I should have shaded this region corresponding
Oh,
to.
so it's always a rectangle.
Yeah, it's always a rectangle.
Why is that?
So the way I see it, so you can sort of imagine particles for the spinons pinned here. So you can sort of, when you scatter from here, you can scatter here with momentum q almost 0. Or you at most scatter here with momentum 2pf. And there is no constraint in the omega direction. So you sort of, so in the omega direction, you can do whatever you want. But here you're bounded to pf, and so you were.
Why is there no constraint in the omega direction?
Yeah, because
I thought if I were forced to have
so
omega, I'd have to have it.
so exactly, so that's what happens here, for example, right? So for and this is because of this. So you sort of define when you integrate, usually have this let's say e2 over k, and so this will be defined as d k, and yes, some angular, right? Yes, some angular average. So this is how you do the integral, and when you define these on-shell distribution functions, you will also deal with delta of chi of k, which means that this will put all the Fermi functions directly, okay, on the Fermi energy, whatever. And so you see here, while usually you have delta of omega minus k, here you just have a delta. Okay, so here you keep some constraint on omega, while here no. And yes, so this is Fermi liquidity. And here's an effect. Non-Fermi. Yes.
Other questions? So let me try to understand what you're saying. So you've got an upper layer that induces a drag in a conducting layer that's beneath the spin liquid, like mediated through the middle.
Yes.
What would happen if I created a circulating current in the upper layer? Rather than a linear current.
I don't know, I think
So this is something I'm very interested actually, so I want to know your answer.
I think we will whatever you do in the upper layer momentum still transfer the information, I guess, not changed to the lower layer. Yeah, I think
So this is a divergence-free current.
so. We can I don't know. So if you think about it this way, okay, then maybe you also so I don't know if you sort of introduce some sort of relaxation, but then I don't know, if you introduce some sort of two-dimensionality, then I think you could still do it.
Would I induce a circulating current on the lower level? That's my question to you.
I would say
Okay. All right, thank you. Any other questions? Okay. Great, let's thank you. Okay.